Сейчас иду в поход в лес и там чуть-чуть позанимаюсь физухой и сделаю пару комментариев. Взял с собой рюкзачок и можно будет пообщаться на интересные темы.
You see, a single cable was simply too big to have been carried by one ship.
Итак, что мы имеем? Heavisade первый получил выражение для силы, которая действует на заряженную частицу, движущуюся в магнитном поле. И в 1889 году в журнале Philosophic Magazine он опубликовал статью, где среди прочих результатов была приведенная формула. Вот сама формула. Что же сделал Heavisade уже в первые годы своей работы? Он ввел понятие потока электромагнитной энергии. Несколько раньше, независимо от Heavisade, это понятие ввел Пойтинг. Heavisade тогда не знал работы Пойтинга, вышедшей на несколько месяцев раньше. Но он пошел дальше Пойтинга и разобрал ряд случаев, важных для понимания, в которых энергия переносится полем. В частности, он рассмотрел выделение тепла в проводнике при прохождении электрического тока. Heavisade показал, что это тепло создается за счет энергии поля, окружающего проводник.
Okay, so what we've got here is the equivalent circuit of a long transmission line. If I send a pulse from a Morse key, then you can see on the upper trace of the oscilloscope the pulse from that Morse key. And if you look at the output, it looks as though nothing has been received. So if we now magnify the received signal by a factor of 10 and do that again, there's the transmitted signal as a nice square wave, and we can just begin to see the start of a received signal appearing at the other end of the line. Now that is with this trace magnified by 10 compared to the upper trace. Let's increase that now to 100 and have another look. And this time we can see that there is a signal being received, but not only is it very small, it's also no longer a square wave. Instead of nice sharp edges, the waveform has actually been spread out and is far more curved in appearance. The spreading of the pulses is a problem because when you're transmitting, the speed of your transmission, you can find that one pulse, one dot, will merge into a second and a third. So whilst you might be sending 3 dots, the letter S in Morse code, actually what you might receive at the other end would appear to be just a single continuous waveform or a dash. And that means that you're going to have to transmit at a far slower speed with a long transmission line. So Oliver Heavisade did a more complete analysis of transmission lines, and he discovered that what really matters is that the resistance, the conductance, the inductance and capacitance need to be in a specific ratio. And if you can achieve that ratio, this spreading effect of pulses will be greatly diminished. Now with the circuit we have here, we can demonstrate that, because by flicking these switches, this will change the value of the capacitance in this case, so that all the other components match the Heavisade equation. Now let's have a look on the scope what happens when I send a signal down our transmission line. And immediately what you can see is that the input signal, which is still the same square wave it's always been, but the output is now following exactly as a square wave the input. There's no spreading of the signal. We still have attenuation. These two traces are still magnified by 100 times. We still have attenuation, but that spreading problem has been completely eliminated.
Heavisade рассмотрел прохождение переменного электрического тока по проводнику. Он показал, что переменный ток неравномерно заполняет проводник. Величина тока растет по мере удаления от середины сечения и по мере приближения к поверхности. Чем быстрее меняется ток во времени, тем сильнее он прижимается к поверхности проводника. Это явление позднее получило название skin-эффект от английского слова skin – кожа, шкура. Skin-эффект широко распространен, его теория без упоминания имени heavisade имеется во всех учебниках. Умов путем некоторых простых допущений о движении частиц скрытых сред и приняв в качестве исходного пункта закон равенства действия и противодействия, закон взаимности, сумел получить количественное выражение основных законов взаимодействия электрических зарядов, элементов тока, магнитных полюсов, движущихся электрических масс и так далее. Несмотря на некоторую механистическую окраску, вполне естественная дань времени, основным при оценке рассматриваемых работ Умова следует считать то, что в них развиваются идеи о необходимости материального посредника для передачи взаимодействия, то есть по существу полевые представления. Он вводит представление о токах живых сил и по существу о векторе полного тока. Уравнений. Умов рассматривает проблему переноса энергии при взаимодействии тел на расстоянии. В случае, когда взаимодействие может быть описано путем введения потенциала. Сюда относится взаимодействие весомых электрических и магнитных масс.
In his grasp.
В 1884 году английский физик Пойтинг опубликовал знаменитую статью, которая по существу содержала развитие идей Умова применительно к электромагнитному полю. В этом исследовании Пойтинг создал теорию о движении и потоке электромагнитной энергии, которая явилась важным дополнением и принципиально новым в развитии теории электромагнитного поля Максвелла. Пойтинг, исходя из Фарадея-максвеллской концепции близкодействия, цитирую: «Если мы признаем непрерывность движения энергии, то есть признаем, что при исчезновении энергии в одной точке и появлении в другой, она должна была пройти через промежуточное пространство, то мы принуждены сделать вывод, что окружающая среда содержит, по крайней мере, часть энергии и способна передавать энергию от точки к точке».
Okay, so let's consider a simple example of sending a digital signal or a rising edge down from a signal source down to a load. Now the propagation down that line is not going to happen instantaneously. There is a speed associated with it, which is really a function of the dielectric constant. Now this line that we're sending this down could be a trace on a circuit board, it could be a coaxial line, and there's always a return path down through ground itself to ground, or maybe from the center conductor of the coax to the shield. So what's really happening is as we send this voltage transient through this line, we're basically sending current in that's going through this inductor and charging the distributed capacitance as you go along the direction. And that's going to propagate in the other direction with that same voltage and current relationship. So at any point on the line, we have these two voltages, the incident voltage coming in and the reflected voltage coming back, adding up to create a voltage at different points on the line, going up into the scope. And right now I've got the scope terminated into 50 ohms, which is what that generator expects. An amplitude, talk about why that is. And I also see some distortion occurring at our tap point in the middle of the line. So why are both of those things happening? Again, if we take a look at our quick little model here, we're using a signal source that has a output impedance of 50 ohms. So when we initially launch that signal into the transmission line looks like a 50 ohm resistor all the way back. Then the same thing happens on the falling edge. Now of course this could cause some. I move these two signals so it looks like one is the incident wave and one is the reflected wave. You'll be able to see how the sum is staying essentially in place with respect to the other two signals, even though one is moving in this direction, one is moving in that direction. The sum is standing in place, it's just changing in amplitude. Okay, so let's set things in motion and we'll watch. I'm going to simulate the incident wave moving in this direction, the reflected wave moving in that direction, and watch that the sum of them will change in amplitude but won't change in position horizontally. See how that sum is kind of staying in one direction. Let's move it the other way. You can kind of see we get a standing wave essentially of the sum between them, even though the incident wave and reflected waves are moving in opposite directions. So that's what we mean by getting essentially a standing wave pattern on the coax itself if you're not properly terminated, because the reflected wave and the incident wave will add up, but because of the same frequency, as they add up, they create this wave that stands in place but just changes.
People who study waves extensively in the various fields of physics and engineering are impressed by the similarities which exist in the behavior of waves in various mechanical, electrical, acoustical, and optical wave systems. These similarities are due, of course, to the basic fact that waves of all kinds behave fundamentally alike. These two rib-like structures are mechanical wave demonstration machines. With them, I can show you many of the various wave properties which you may have studied experimentally or theoretically, perhaps without ever having actually seen what the waves themselves are doing. The waves which travel on this machine are really waves of twist or torsion, which propagate along this central wire. Attached to the central wire are these cross arms, which translate the torsional motion of the central wire to the up and down transverse motion of the ends of the cross arms, which you see. The entire structure is supported in a set of bearings which permit the central wire to twist freely. This second wave machine is built similarly to the first. It has cross arms which are considerably shorter than those on the first machine, and as a consequence, the speed of a wave along the second machine is about 3 times faster than the speed of a wave along this machine. You'll see later on why I have these two machines. First, I want to show you the two different ways in which waves may be totally reflected. Observe that right now this machine has a free end. That is, this last cross arm is perfectly free to move without restraint. If I start a wave at this end of the machine, that wave travels down to the far end, is reflected there, and returns as a reflected replica of its original self. But now let me terminate this machine in a different way. I'll clamp this last cross arm to a heavy stand so that a wave arriving here can't produce any displacement of the cross arm. This time you see the wave is reflected upside down. The reflection is still total as it was before, but the wave is inverted upon reflection. In a mechanical wave system, then, there are two ways in which the total reflection of waves may take place. Right side up, if the reflecting end of the medium is completely free, and upside down if the reflecting end is completely restrained. Now, if nature has any consistency, and we like to think she does, this alternative reflection possibility should exist for waves of all kinds, and these other drawings here show that indeed it does. Take the case of an electrical transmission line, for example. You know that there are two ways in which electrical waves can be reflected, depending on whether the far end of the transmission line is terminated by a short circuit or by an open circuit. And similarly, in the case of waves traveling down an acoustic tube, there are two different reflection possibilities, depending on whether the end of the tube is closed by a rigid termination or by the acoustic analog of a free end. Note that in the mechanical situation, a clamp is a constraint preventing the displacement of the end of the wave medium. The electrical analog of this state of affairs is an open circuit termination on the end of a transmission line, preventing the flow of current at such a termination. And the acoustic analog is a rigid closure at the end of an acoustic tube, preventing the longitudinal vibration of the air. In all of these cases, the reflected waves come back upside down, and in all of these other cases, conversely, which are analogous to the case of the free end of a reflecting wave medium, the reflected waves come back right side up. You see, nature really is consistent. Well, now let's have a look at some of the other things we can do with our wave machines. One of the most important topics in the general development of wave behavior is the principle of superposition. When two waves traveling in opposite directions on the same medium, as you see here in slow motion, pass through each other, the instantaneous amplitude of the resultant wave is the algebraic sum of the amplitudes of the two constituent waves. This principle of superposition is equally valid when one of the two waves is positive and the other one is negative. Observe that in this case, at the instant of exact coincidence, there is a momentary cancellation of the amplitude, and the medium appears to be undisturbed. Now let's have a look at the superposition behavior of continuous trains of periodic waves. With this small motor and crank, I can generate such a train of waves at this end of the machine and reflect them back upon themselves at this end. All right, in slow motion now, here come the waves. After reflection, the waves travel back up the machine, superposing on the oncoming waves which they meet to produce patterns of built-up amplitude at some places and complete cancellation at others. The pattern that you see on this machine appears to be standing still, doesn't it? The various portions of the medium simply bob up and down in place without giving you the impression of motion in either direction along the machine. Observe that in this pattern there are places where the medium appears to be standing completely still all the time. These dead spots, or nodes, are exactly half a wavelength apart. Now, I'm sure that you've all seen behavior of this kind before. For example, a vibrating string always vibrates naturally in one or more segments separated by such nodes. Now let me show you something else. Suppose I simply move this reflector a short distance up the line toward the generator, just far enough so that the travel time of a wave down and back is an exact multiple of the wave period. Under these conditions, the new waves which are continually being sent out by the generator superpose upon the previously emitted and multiply reflected waves in just the right phase to build up the amplitude to an abnormally large value, new crest on previous crest, and so on. The system thereupon becomes resonant, and the amplitude builds up to the noticeably larger value that you see here. Under these conditions, the new energy which is being fed into the system at each cycle is exactly equal to the energy which is being dissipated per cycle through friction at this new amplitude. Now, the initial adjustment which I made in the length of the machine to produce this resonant condition is called tuning. I could just as well have produced resonance by leaving the line at its original length and tuning the frequency of the generator instead. And I can destroy the resonant pattern that I have here by changing the value of either of these parameters a little bit in either direction. Another way of looking upon a resonant system is to regard it as a reservoir for energy. Thus, the escape wheel of a watch, a child's swing, a sounding organ pipe, the resonant circuit of an electrical radio transmitter are all examples of resonant systems. They exhibit abnormally large amplitudes of oscillation, and they possess relatively large contents of energy which have been built up by superposition over many previous cycles. Now, from here, I want to go on to the subject of the impedance of the wave medium. The generation of waves on a transmission line of any kind, electrical, optical, or what have you, involves two parameters, an originating cause and a resulting effect. In an electrical transmission line, for example, the cause of the waves is an AC voltage applied to the input end of the line, while the result is an AC current flowing into the line. The ratio of the cause to the effect is called the impedance. You're probably most familiar with the term impedance through your studies in the field of electricity. But this impedance concept is just as applicable to wave systems of other kinds as well. On our mechanical wave machine there, for instance, the cause of the waves is the oscillating torque which I apply to the first cross arm, and the result is the oscillating angular velocity imparted to the medium. On that structure, then, the impedance, the mechanical impedance, is the ratio of the applied torque to the resulting angular velocity. In terminating the other end of a transmission line, we frequently seek to adjust the impedance of the terminating load to equal the impedance of the line itself. When this is done, all the wave energy traveling down the line is absorbed by the load and no reflection takes place. The load is then said to be matched to the line. Now, this matching condition can be demonstrated very nicely with the wave machine here by attaching to this last cross arm a mechanical impedance and adjusting the resistance, the counter torque, with which that impedance reacts back on the motion of this cross arm. Such a mechanical impedance is afforded by this dash pot, simply a tin can full of water with a little piston pumping up and down in it. By sliding this dash pot in or out along the last cross arm, I can control the counter torque with which it resists the displacement of the medium, and thus match the impedance of the dash pot to the impedance of the transmission line itself. When this adjustment is properly made, the dash pot absorbs all the wave energy that travels down the line, and as you can see, hardly any perceptible reflection takes place. Now, instead of using single waves, suppose we have a look at this behavior with a train of continuous waves. Here you see such a train of waves traveling down the machine from the generator to the load and disappearing into the dash pot. Now suppose I spoil this nice matching adjustment by moving the dash pot farther in toward the central wire. The impedance of the load now no longer matches the impedance of the transmission line, and a partial reflection of the wave energy occurs. Let's have a look at this partial reflection now with continuous waves instead. We expect some kind of standing wave pattern to appear on this machine now, don't we? After all, we have running waves going in this direction and returning waves coming in this direction of the same period on the same medium, only this time the returning waves have the lesser amplitude because the reflection down here is only partial. Well, I do see a standing wave pattern of sorts. Here are the nodes, half a wavelength apart, only notice now that the nodes are no longer standing still as they were in the case of 100% reflection. Suppose I have the camera speed up the picture for you so that you can see what the envelope of this standing wave pattern looks like. Now let me draw you a sketch of that standing wave envelope. The amplitude at this point I'll call A sub maximum. At this point, A sub minimum. Now in wave theory, the ratio of A max to A min has a particular significance. It is called the standing wave ratio, abbreviated SWR. On the wave machine, the standing wave ratio is about 3 to 1. Now recall that when we had 100% reflection, when the end of the machine was clamped, we obtained a standing wave pattern with motionless nodes. The standing wave ratio in that case was infinity. On the other hand, when I had a perfect impedance match, there was no reflection at all and no standing wave pattern. In that case, A max and A min were the same, and the standing wave ratio was unity. Now I think you can begin to see where I'm leading you. The punchline is this. In any practical case of reflection, a measurement of the standing wave ratio on the medium just ahead of the termination enables one to calculate the percent reflection that is taking place there. The complete expression is percent reflection is equal to the standing wave ratio minus 1 squared divided by the standing wave ratio plus 1 squared times 100. Now, just for fun, let's measure the percent reflection that's taking place here. With these identical scales, I can measure the amplitude at a maximum and at a minimum of this partial standing wave pattern. Maximum 5, minimum 2. If you and I agree, the maximum amplitude we saw there was 5 units, while the minimum amplitude was 2 units. Therefore, the standing wave ratio is 5/2. Substituting in the percent reflection formula, we obtain percent reflection is equal to 5/2 minus 1, which is 3/2 squared, divided by 5/2 plus 1, which is 7/2 squared, which gives us 9/49, or about 18%. Now note that I have just calculated the percent reflection on a mechanical wave system using an expression that was first developed in the field of AC electricity. Now, this is a perfectly valid and logical thing for me to do, since waves of all kinds behave alike. Now, let me develop for you another idea. Waves are partly reflected not only at mismatched terminations, but also at places where the impedance of the transmission medium changes abruptly. Suppose I connect these two wave machines end to end. Together, they give me a single transmission line made up of two pieces having different impedances. At this point, where the two central wires are clamped together with this little clamp, there is an abrupt discontinuity in the impedance of the transmission path. A wave traveling slow along this medium will suddenly speed up when it crosses over into this one. This behavior is similar to what happens to a beam of light when it emerges from glass into air. Now, before I show you what I want to show you, let me clip this dash pot down here in a matching position to prevent the unwanted reflections from this end. It's this point here that we're really interested in. All right, here comes a wave. And there it goes. Again. Do you see the reflected waves coming back from the midpoint here? Now that I've warned you what to look for, this time you watch for that reflected wave coming back. Here it comes. And once more. There goes the main wave. Here comes the partly reflected wave. You know, our world simply abounds in examples of this kind. Electric waves, light waves, sound waves, mechanical waves are partly reflected when they encounter impedance discontinuities. Usually in situations of this kind, however, continuous waves are involved. After I connect up this motor, we can see what happens when continuous waves meet an impedance discontinuity. As we might expect, a partial standing wave is produced. If I wanted to determine how much energy is reflected there, I could measure the maximum and minimum amplitudes of the envelope and calculate the percent reflection by the standing wave ratio method we used before. That expression is equally good for calculating the energy loss at any kind of impedance mismatch or discontinuity. Often in our technology, this partial reflection of wave energy by impedance discontinuities in the transmission path is economically wasteful, and we seek to avoid it by inserting some kind of impedance matching device between the sections of the medium bordering the discontinuity. Here is an example of such a mechanical impedance matching device. It is simply a short section of the wave medium, exactly a quarter of a wavelength long, and having a cross-arm length intermediate between the cross-arm lengths of the two machines. It is called a quarter wave matching transformer. I'll sandwich it in here and then show you how it operates to promote the transmission of wave energy across this discontinuity without reflection loss. All right, here come the waves, and now you watch what happens. And there they go. There is no perceptible partial standing wave on the input portion of this transmission system, as there would be if reflections were coming back from the junction. Apparently, then, I have matched the impedances of these two machines. This kind of transformer has a direct analog in optics. The non-reflecting coating on the lens of this camera is an optical quarter wave matching transformer. It works in precisely the same way with light waves. Now, unfortunately, this type of transformer suffers two major drawbacks. It operates only for continuous waves, and it is effective only for a narrow range of frequencies, including the particular one for which it was designed. For applications in acoustics, mechanics, shortwave radio, and the like, where it is desired to accommodate much broader ranges of frequency, we have a different kind of matching transformer, to which this megaphone is a first approximation. Now, the megaphone smooths over the impedance discontinuity between the air column in my throat and mouth and the free air in the space around me by means of a gradual taper. The mechanical analog of a megaphone is a section of the wave medium whose cross-arm length at the two ends matches the cross-arm length of the two machines that I am trying to couple together, with a gradual taper in between. A tapered section transformer such as this will match impedances over a relatively wide band of frequencies. It is effective also for use with single waves and pulses. Watch what happens now when I send a number of pulses down this line. Here comes a short, quick one. And you see that hardly any perceptible reflection comes back. Here comes a somewhat longer one. And again, only a small amount of reflection returns. You see, the tapered section transformer is really a relatively broadband device. Here is another example of a tapered section transformer. It is a piece of waveguide used to couple a section of rectangular cross-section waveguide to another one of a smaller cross-section in such a way as to prevent the reflective loss of radiation. In electricity, we employ transformers ranging all the way in size from this little fellow you can scarcely see, clear up to the big transformers almost as big as houses that you find in hydroelectric stations. Even nature herself is in there pitching. Inside the mammalian ear there are three tiny bones called the hammer, the anvil, and the stirrup. Their task is to provide an impedance linkage between the low impedance of the air in the outer ear and the high impedance of the liquid in the inner ear. And in addition to all these transforming devices that are used with pulses and waves, there are others that are employed with unidirectional motion. For example, in mechanics, all of the mechanical advantage machines such as gear trains and levers and pulleys and the like, are really impedance transforming devices. Now, in this film, I hope I've been able to present you some different approaches and perhaps to lead you to a few new insights. One thing that has always profoundly impressed me is this: waves of all kinds behave alike. And if through any process you choose, you can learn the fundamentals of wave behavior, either through the study of some discipline in which waves play an important role, or even through the study of waves for themselves alone, then you will always feel at home in any branch.
Итак, смотрим. Закон взаимодействия электрических зарядов. Так, мы видим эксперимент, который проводил Кулон с крутильными весами. И теперь посмотрим, что называл Кулон как неким зарядом. Мы видим, что зарядом называется, да, по сути-то, два наэлектризованных тела, которые притягиваются либо отталкиваются друг от друга. Понятие в электрическом поле. При исследовании взаимодействия электрических зарядов, естественно, возникает вопрос, почему появляются силы, действующие на заряды, и как они передаются от одного заряда к другому. В процессе развития физики существовало два противоположных подхода к ответу на поставленные вопросы. При одном из них предполагалось, что телам присуще свойственно действовать на другие тела на расстоянии, без участия промежуточных тел или среды, то есть предполагалось, что силы могут передаваться от одного тела к другому через пустоту и притом мгновенно, теории дальнодействия. С этой точки зрения, при наличии только одного заряда никаких изменений в окружающем пространстве не происходит. Согласно второму взгляду, силовые взаимодействия между разобщенными телами могут передаваться только при наличии какой-либо среды, окружающей эти тела. Последовательно от одной части этой среды к другой и с конечной скоростью, теории близкодействия. Фактически то, что начал изучать Умов. Даже при наличии одного единственного заряда в окружающем пространстве происходят определенные изменения. Согласно современная физика сохраняет только идею близкодействия и отвергает дальнодействие. Электрическое поле заключает в себе и переносит определенную энергию, а также обладает импульсом и массой. Следовательно, электромагнитное поле не есть абстрактный образ, введенный нами для описания электрических и магнитных взаимодействий, но представляет собой объективную реальность, обладающую физическими свойствами. Оно является определенной формой материи, которая осуществляет электрические и магнитные взаимодействия. Таким образом, современная физика при помощи понятия поля расширяет представление о близкодействии и распространяет его на немеханические явления.
The theory that a flow of electricity could in some way create an invisible force field was originally proposed by Michael Faraday.
And as something that can occur in waves.
Вот. Что мы еще раз говорим, что поля имеют электромагнитное поле, заключает в себе и переносит определенную энергию, а также обладает импульсом и массой.
Surface of water with your finger, changing the direction of the electric current.
Электромагнитное поле, которое обладает и импульсом, и обладает массой. И что нам говорил товарищ Эйнштейн о том, что фотон не обладает массой, да? Почему? Потому что если тело разогнано до световой скорости, оно массой обладать не может. При этом мы видим противоположную картину. Вот. Точная проверка закона Кулона. Это эксперимент, который провел Кавендиш. Что здесь написано? Поэтому, исследуя на опыте, действительно ли в объеме проводника нет зарядов, можно проверить справедливость закона Кулона, и притом гораздо более точно, нежели в опытах с крутильными весами. Такие опыты провел впервые Кавендиш, который за несколько лет до Кулона установил, что сила взаимодействия зарядов обратно пропорциональна квадрату расстояния. Вот такой опыт.
Maxwell's maths was so advanced and complicated that only a handful of people understood it at the time. And although his work was still only a theory, it inspired a young German physicist called Heinrich Hertz. Hertz decided to dedicate himself to designing an experiment to prove that Maxwell's waves really existed.
Войдите. Райка, ты? Как хорошо, что ты пришла. Сейчас я тебе покажу новые приборы. Никаких проводов нет. А смотри, что получается. Вот сюда смотри.
Извини меня, но я ничего не вижу.
А, ты лупу возьми.
Да, крохотная искра.
Ага. Искра-то крохотная, но какая в ней великая и плодотворная сила. Странно все-таки. Такие крупные ученые, как Герц, Ри и Лодж, считают, что электромагнитные волны никакого практического применения получить не могут. Неверно. Глубоко неверно.
Можно? Ну вот, Александр Степанович, доставил в целости и полной сохранности. Пожалуйста, прошу вас.
Хорошо. Очень хорошо. Можно начинать?
Можно. Только, Александр Степанович, а не присесть ли нам, а?
Как перед большой дорогой.
Вот-вот.
Ну что ж, присядем.
Ну-ну. Ну вот, начнем?
Начнем. Включаю.
Звонит! Звонит! Звонит?
Попробуем еще раз. Только отойдите, пожалуйста, подальше.
Ага. Хорошо. Я готов. Можно.
Включаю.
Звонит? Великолепно.
Будьте добры, Петр Николаевич, отойдите, пожалуйста, еще дальше.
Ага. Я тогда в класс пойду, Александр Степанович.
Хорошо, идите.
Я готов, Александр Степанович.
Включаю.
Звонит! Я иду еще дальше.
Идите, Петр Николаевич.
Готов, Александр Степанович.
Включаю.
Звонит.